Why not? So we've got the screen share. Can everybody hear me on the Zoom world? Okay, cool. Hopefully you guys can hear me as well. Yeah. All right, rock and roll. So we still are in Lecture 3, Example 3. Big picture of this unit is learning how to describe the effects of predictors that take more than one slope to describe their effect. That's the big picture. So the first instance of that we saw was a predictor that is categorical, that has more than 2 groups to it, 2 categories. We end up having to make number of dummy-coded predictors, that's number of categories minus 1, and put them in the model. So if I have 4 groups, you need 3 new predictors. If I had 5 groups, you need 4 new predictors, that kind of thing. And that corresponds to section 1 of your homework that's up right now is an empty model, which you've done before. Section 2 is that. So hopefully by the end of today, you'll be able to do the whole thing whenever you feel like it. We have one more example to go through, and then that will be done. And the next I'll save for the subsequent homework. So anything that you want to talk about as a group before we dive back in or review? Points of clarification I can help with?
Yeah, actually, I have a quick question.
Hit me.
So the homework is due, I believe, the Monday after spring break. Is that correct?
No, the Monday after the Monday after.
Okay, that makes a lot of sense. Thank you.
Yeah, I thought about having it due the Monday after, and I thought, what am I doing? Like, this is the worst idea ever. So it's not due until the 28th. But that yeah, but the rest of the course then, like, I think you have something every week until the end because I've pushed everything as far as I can that way. So yeah, you have like 2.5 weeks or something. But I just want to let you know, like, when you are able to do it. Like, right now you know enough to do 2/3 of it, and hopefully by the end of today you can do all of it whenever you feel like it. Other questions or things we want to go over? All right. Well, let's jump back in. Let me see here. We have done all the group stuff. We talked about F, sums of squares. We'll talk about that again today in another context. I think we're ready to do intermediate summary and then change gears a little bit. Sound good? This is slide 23. Let's pick up there on example or lecture 3. So summarizing what we've done in this unit up to this point. So for general linear models with one fixed slope, the significance test for that slope is the exact same thing as the significance test for the model. So for instance, if I have one quantitative predictor and I want to look at a linear relationship for it, then I can test that slope for the linear relationship against a null hypothesis, usually 0, divide by the standard error, and that gives me this thing that's t. So t is a test statistic, and otherwise known as t-value, because that is a lot easier to say, especially with the mask on. And if I compute an effect size for that slope as a Pearson correlation, so the standardized slope as it is known, works out to be the exact same as Pearson's R. And if I square that correlation for that single slope, that's R squared for the model. So there is a 1-to-1 correspondence between model and slope if you only have one slope. If you have more than one slope, that's where they diverge. So for GLMs with 2 or more fixed slopes, so such as the case if we have 3 groups, for instance, the significance test of those slopes or any linear combinations to get differences between the non-reference groups are not the same as the significance for the overall model. We need both. So we still have a significance test and an effect size that we need to quantify for each slope, but in addition to that, what we want to know is whether the slopes work together successfully to predict the outcome. So we can think of that in a couple different ways. If I compute y hat as a variable, so what the model says my outcome should be for everybody, and I have my real outcome variable next to it, I can do a correlation between those. If I take that R correlation and square it, that's R squared for the model. The other way to think about an R squared for the model is let me say it backwards. By what proportion did the residual variance get reduced by adding your slopes? So the difference in the residual variance should come down because that's the unknown part. There should be less that's unknown and more that's known. So R squared tells you by what proportion the residual variance was reduced. Said more simply, how much was explained? So words to put together in your head: explained, accounted for, predicted by the model. Like reasons that we know why some people have a different outcome than other people. That's one pile. And then the other pile then is unexplained, leftover, remaining, residual, unaccounted for. So we end up with an effect size for how good the model works in predicting the outcome is R squared, and a significance test that goes with that effect size via F. And if we're not using denominator degrees of freedom, it would be chi-squared. So that happens in my other class, for example. Okay, any questions on any of that vocabulary or concepts? So the context in using this stuff before was a grouping variable in which we had multiple slopes to differentiate all the groups. Let's change the story, but do the same thing. So what if I have a quantitative predictor and I hypothesize, or the data suggest, that I need a nonlinear relationship? That could happen. So if I think about as x goes up, y goes up. But is there a point at which, like, as x goes up, y doesn't really change anymore? Like diminishing returns? Like studying for an exam, at some point, like more effort is just not going to help you, right? There's like a curve to it. Or is it possible that something makes it worse at higher levels instead of more? So the relationship between, say, like arousal and performance, right? If you don't give a shit about something, you're going to do very badly. If you stress about it way too much, you're probably going to do badly. There's a sweet spot in the middle where if you care enough, that's when you're going to get your maximum performance potentially. So those are all nonlinear relationships. So I want you to be able to specify models to test those. And this is yet another instance in which a Pearson correlation is not going to be adequate. Pearson correlation captures linear relationships. So we need to do something else. So curvilinear is one type. For instance, we're going to learn today about quadratic slopes, which is created by taking a predictor variable and squaring it. You can also do a log transformation of a predictor to create what's known as an exponential curve. I'll show you pictures of those. And then piecewise effects. So what's known as a linear spline in other disciplines, the idea that maybe you need a different slope for each different section of a quantitative predictor. We're going to look at an example with education, where we look at whether one more year of education has a different impact if you're going from 7th grade to 8th grade than if you're going from 13th grade to 14th grade. So those are all examples of nonlinear types of relationships in which we're going to need more than one slope to capture the effect of a predictor that has a nonlinear relationship for the outcome. And last but not least, what to do with ordinal variables and whether or not you can treat them as interval. That's a special case of this as well. So quadratic, first up. This is very common, and it's probably because of its ease of being specified in most software packages. So a quadratic relationship is a U-shaped relationship, or a parabola, as we may have learned it in math once upon a time. So up to this point, if we've had a quantitative predictor, we put the quantitative predictor in, we center it, right, so that the intercept means something. I'm talking about adding an additional term that is that quantitative predictor squared. So both the original linear effect and the squared term are needed to create what's known as a quadratic relationship. And this type of model is good for effects that change directions. So x goes up, as x goes up, y goes up to a certain point, but then as x goes up, y goes down, or vice versa. So the model would look something like this, where x is my quantitative predictor. I have beta 1 that gives me the linear slope of x, and beta 2 that gives me what's known as the quadratic slope, so the squared term. That's one example. Another is exponential. So this is actually a trick, a hack, as it were. Maybe I can make a TikTok video and dance and talk about this as a hack. Yeah, no. The internet does not need that. But in this case, the hack is that we're going to take the predictor and do a natural log transformation of it. A natural log transformation takes a predictor that is positively skewed, so it has a long right tail and kind of reels it in. And it also takes like something that's piled up between 0 and 1 and stretches it out. And the end result, if you take your model and put in the logged version of the predictor, is that beta 1 captures an exponential curve, meaning a diminishing returns kind of curve to it. So the log is a way to get that in a linear model much more easily than fitting a nonlinear model. So a couple of examples of that. The tricky part with quadratics. There is a rule that you have to learn to interpret a quadratic coefficient correctly. And the rule is multiply it by 2. Cough, cough, homework question. That's the trick. So a quadratic effect of a predictor implies that the slope of that predictor changes across the levels of the predictor. The slope that you get for the squared coefficient itself, the beta 2, is actually half of what is known in physics terms as the rate of acceleration or deceleration. So linear is like velocity, quadratic is like acceleration, except the slope that's given to you directly is only half of that. So to get to the full amount of acceleration or deceleration, you have to multiply it by 2. So for example, if I have, why do I have dollar signs on my equation? Do you have dollar signs on your equation?
No.
Okay. Well, you know why I have dollar signs? Because that's where the money is, folks. You learn how to do this, someone's going to pay you. So it's just reminding me. So here's my function. Let's say that I'm predicting something and my intercept is 50. The slope coefficient that goes with x is 4, and the slope coefficient that goes with x squared is 0.3. Just making up some numbers here. If I were to compute what the slope is at any given point of x, what I'm actually talking about is finding the first derivative of this function, and it would be the linear slope plus twice the quadratic slope, because the 2 comes down when you differentiate. And if I were to find the second derivative, which is the rate of acceleration, it's just twice the quadratic. So for those of you who remember calculus or physics or any of these concepts, this will make sense. If you're like, yeah, Lisa, calculus was like 30 years ago, don't talk to me about it anymore, cool, just multiply it by 2, because math. And that's all the explanation you need. There's another way that I can explain it, but we haven't talked about interaction terms yet. But by the rules of interpreting those, this works for the same. So let me show you some pictures, because pictures make everything better. There's really only 4 kinds of possible patterns of quadratic slopes. And you can describe them by what happens to the linear slope as you increase along the predictor variable. A quadratic slope can take a slope that's positive and make it more positive, make it grow, or it can make it slow down and become less positive. Likewise, it can take a slope that starts out negative and slow it down, or make it grow and become more negative. So those are the 4 possibilities that I've got on the screen here. So this is a slide actually from my longitudinal class, to be offered in the fall again, where time is the predictor variable that we're talking about in this example. So this line right here was created using a function in which the linear slope of time is 4, and the quadratic slope of time squared is a positive 0.3. These tiny little lines right here are meant to convey what the slope is at each subsequent occasion. So for every 1 unit change in x is like moving up 1 more unit in time. So at 0, right here, the slope is 4. At this point, for those of you who remember best up, this is the line that's tangent to the curve at the point. That's what I'm trying to draw here. So it is, for every additional unit of time, y goes up by 4 at this point. But the line doesn't stay constant with respect to the slope, it changes. And if I have a quadratic that's positive paired with a linear slope at time 0 that's positive, then what happens is that as we move up 1 unit in time, the slope becomes more positive by twice the quadratic. So the slope at this occasion is 4.6. At the next occasion, it grows by twice the quadratic again to be 5.2, 5.8, and so on. So the slope is increasing. There is a bigger change over time the further up in time you go. So this would be like bacteria growth on a sponge or something that like takes off in this sort of positive accelerating fashion. The slope is speeding up as time goes on. A 1 unit change in time has a bigger effect on the outcome later than it does earlier. So this highlights a couple of things. The way that we talk about the linear slope is that it is conditional on x equals 0. That's the other part of it, is that this is no longer the linear slope period, it's the linear slope at a particular occasion when x is 0. So it becomes conditional just like the intercept does. Okay, with me so far? Okay, move into the top right panel. Starting at the same point, a positive linear slope at time equals 0 of 4. But now it's being paired with a negative quadratic slope, which is the slope of time squared. So now my positive slope is becoming less positive as time goes on by 0.6, because that's twice the quadratic. So the slope is slowing down. So by the time I get out to time 5, the slope is only 1. And what do you think is going to happen to it if I were to keep going according to this model? It's going to fall off. It's going to come back down. So these models with quadratic terms do predict that what goes up must come down and what goes down must come up. The question is, over what range of the data are you likely to see each piece of it? So I would call this first left picture a linear slope that's positive, that grows more positive as a function of the quadratic. I would call this picture to the right a linear slope that's positive that grows less positive. Down here, these are negative slopes. So again, starting at time equals 0, a slope of -4 in both pictures. But what happens to it as a function of the quadratic slope, which is the multiplier of time squared, depends on the sign. So if I pair a negative linear slope with the positive quadratic, then it is slowing down the negative, making it less negative. Whereas if I pair it with a negative, then it's speeding it up. So this bottom right picture, to me, looks like what would be known in the cognitive aging literature as terminal decline. Like you have something catastrophic happen to your health or your brain and everything just sort of falls off the cliff. A morbid example, but that's what it is. Something like this up here might be learning over time, like eventually the rate of learning slows down, although a quadratic model would predict that you lose your learning, and and that may not be the case. So sometimes it does feel that way, to be fair, yes, but in a perfect world, you would not lose your learning and come back down. You would stay at the top. So this is a way to make a bendy line, basically. And you can describe it in these sorts of ways. Eventually, if you follow the line far enough, each of these makes a U shape. So this one, if you follow it to the left, will come back up. This one, if you follow it to the right, will go down. This one will go down. This one will come back up, and so forth. So multiply the quadratic slope by 2. That's how you interpret it. That's the trick. Times 2. So when might we fit a model like this? Well, I'm still playing with the same general social survey data from 2012. And although I have selected a subsample out of these data, they are real data. I didn't mess with them, in other words. So to try and get an example of what I might do with prediction by age, for instance, I made this plot in SAS by calculating the mean income for every 2 years of age. So I rounded age into 2-year bins just to make a picture. And the black line shows the mean income for each of these ages, and the red lines show the mean plus or minus a standard error. So this picture's kind of noisy, but it looks like a U to me, where in this sample, the people who make the most money are middle-aged. Hooray! And then eventually you lose your income again, although with quite a bit of variability, as you might imagine. So I'm going to fit a quadratic model to age. Given that the lowest age that I have in my data set is 18, I'm going to center age at 18 so that the linear slope refers specifically to the change in income at age 18, and then we'll talk about what happens to it as time goes on. So just looking at this picture, which of the 4 pictures does this look like?
Second one, positive linear slope, negative quadratic slope.
Yeah, the top right picture, positive linear slope. So at this point of the function, it looks like there's a positive slope. But as you follow the function along, that positive slope goes flat and then eventually changes directions. So I'm expecting to see a positive slope at age 18 paired with a negative quadratic that slows it down and eventually brings it over here. So here's my model. I'll show you how I made SAS, Stata, and R do this for me in just a second, but this is the equation. So note that I have 2 slopes, one for the linear effective age and one for the quadratic effective age squared. We need both. So it may seem redundant, but the quadratic coefficient is only the rate, half the rate of acceleration if the linear is in there too. They work together. So my intercept. Reviewing vocabulary, what's an intercept? Someone give me a definition. I'm watching the chat or I'm listening with my ears. Yeah, predicted outcome when x is 0. So given my centering choice, my beta 0 fixed intercept is the expected income for an 18-year-old. And in this sample, that's $2,600 a year. Seems kind of low, but maybe they work at Walmart, tucking shoelaces into shoes, which is what I did at age 18. I'm not kidding. I made $5.25 an hour to go up and down the shoe aisle at Walmart and tuck all the shoelaces back to the box and make sure that the right toe was up and the left toe was down in the box. And then I vacuumed and unpacked the boxes and threw away all the tissue paper and crap that comes inside the boxes. So yeah, $2,600 a year sounds about right. That was me at 18. Now I have a standard error of 1.5 next to it, so that means that on average, this predicted mean for an 18-year-old would be off by 1.5 from what it's supposed to be across samples. And I have a p-value here for completeness, but no one cares about it in this context. This p-value means that the 18-year-olds are making not $0, because it's tested against a null hypothesis of 0. So significance tests for intercepts are rarely of interest. Okay, with me so far? Okay, so this is like my jumping off point. Remember, the intercept is like the where you are here sign of the model. So now let's talk about what happens to income in people who are older ages. It's cross-sectional, so I can't say it's aging, but I can say it's age differences. So the linear slope. The slope of age right here is specific to when this age predictor is 0. So beta 1 refers specifically to the slope at age 18, the same as the intercept. So both beta 0 and beta 1 are conditional on age 18 because that's where 0 is in my model. So beta 1 then, if I go back to my picture, is the slope right here. That one, specifically. And that's why you have to be specific to say it's at age 18, because what the slope ends up being at any other age is different, right? It's a curvilinear function. The slope is constantly changing across. So this slope of beta 1 was estimated to be 1.2. So that means at age 18 specifically, for every additional year of age, you're predicted to make $1,200 more. And I know that sounds crazy, because it's at 18 and it's per year, but both of those are true at the same time. Standard error of 0.14 tells us the expected inconsistency of that across samples, and p is less than 0.001. So I would call this a significant slope and a significantly positive slope. So more people who are older make more money, essentially, when evaluated at this point on the function. $1,200 per year, because we're in thousands of dollars. Now the quadratic. It's half the rate of acceleration or deceleration. The estimate of it is minus 0.02. So it's exactly as we would have expected from the picture. This linear slope is becoming less positive because I have a negative quadratic that's bringing it down. So to talk about what happens to the linear slope as a function of this quadratic slope, we've got to multiply it by 2. So here's how we would make predictions for other ages besides 18. What about age 30? Even though my model is centered with a reference of an 18-year-old, it tells me what the predicted income is for any age. So if I want to know what y hat predicted outcome is given x equals 30, that's for a 30-year-old, then I start with my fixed intercept for everybody, my linear slope for the effective age, and I put a 12 in here. So why is it 12 and not 30?
Because it starts at 18.
Yeah, it starts at 18. So 18 is 0 at this point. So it's 12 because 30 is 12 more than 18. And then 12 squared goes in here for the same reason. So it works out to be 14.54, which I could have calculated in my calculator, but doing it in the programs will also give me the right standard error to go with it. Likewise, 50-year-old, I plug in 32 because 50 is 32 more than 18, and 70-year-old. So you can see from these predictions that income is supposed to go up to a point, but then it starts coming back down in the older ages. That's the negative quadratic bringing the curve back down. So now a slightly extra level of difficulty. Back up here. This is the slope at 18. Could I figure out, do you think, what the slope is, say, at 30 or 50? Yeah, because I know that the slope changes by twice the quadratic per year of age. So the math looks like this. The predicted linear slope at age 30 starts with whatever the linear slope is at age 18, and then multiplies twice the quadratic times the year that you want the slope for. And no, you will not have to do this on your homework. But if you take longitudinal with me in the fall, you will have to do it there. So I want you to have at least seen it before. So it works out to be 0.75. So at age 30, for every year older you are, you make $750 more. So the slope was 1.2 at age 18. It's slown, is that a word? Sure, it's slowed down. I probably got that from my son too. He says things that to me at this point I can't differentiate from regular English. Like, I told him all about it. Like, telled sounds completely fine to me. So I told you that the slope slowed down to 0.75. Same thing at age 50. The slope has not only slowed down, but it has turned around. So now we're heading back down the hill on the other side of aging. And at 70, it's a negative slope. And there is actually a formula by which you can figure out where the top is, and it turns out to be age 48. So in this sample, the maximum income, the point at which the linear slope hits 0 exactly, is the top of the function, is at age 48. So only 4 more years to go, and I'm rich. Just got to keep riding that function, and then find a way to hop off before I slide back down the other side. All right. So how'd we do? Pretty darn good. So I drew the same plot with the means for each age, and I put the predicted line through it that's given by this model. It does a pretty good job of fitting this, I would say. There's, you know, some weirdness out here for the 65-year-olds, but whatever. Now, is this a good enough model? Well, the plot on the left is telling, maybe not, because these are the residuals. So these little dots are the real data. They're showing you basically how far away from the line each real data point is, where the difference between the dot and the line is E. So the E residual is the deviation from the line to the dot. So like these people up here would have positive E's because they're way above where they're supposed to be according to the model. And the poor people down here are making even less money than the model thinks they should. So there's 2 sets of lines around the prediction. One is this shaded blue right here. And do you see how it gets wider at the end? That's because there's more uncertainty of prediction the further away you go from the mean of the predictor. The dashed lines that are far, far away are taking into account the variability of the E's too. So they're showing you like a much wider range of what each predicted score would be if you accounted for the unresolved variance in the model.
Can you say what the shaded area is again?
This part?
Yeah.
This is it is a confidence interval around the prediction that's given just by the linear and quadratic slopes of age. So like a y-hat confidence interval. The other one is a y confidence interval that also includes E. So that one's way bigger. So I can ask for significance tests for each of these slopes. I can test whether the linear slope is different than 0, whether the quadratic slope is different than 0, but I have to put them together if I want to answer the question, does age predict income significantly? Because how age predicts income is characterized by 2 slopes, not 1. So what am I talking about then? How do I answer that question? How does age predict income overall? What do I need to do? What letter? What? I'll put it up here.
R.
Yeah, R is the effect size. And what's the significance test that goes with the R? Of the slopes working together. F, yeah. So this is our friend F. F is a ratio of what you know over how many slopes it took to know it, over what you don't know, over how many slopes you could have put in. So F has 2 different degrees of freedom that you have to report. The first is called numerator degrees of freedom. That's the 2. That's the number of slopes. The second is called denominator degrees of freedom, and that's the number of slopes remaining given n minus k. So in this model, I have 734 people. I have 731 here because I spent 3 fixed effects, the fixed intercept and the 2 slopes. I could add 731 more things. Slopes, things. F is 47. So I don't need to get out my critical table to tell you that that's going to be a significant F. If my model was crappy and my slopes basically had nothing to do with my outcome and didn't help at all, F would be 1. Possibly even less than 1. That means I did worse than chance if it's less than 1. but it's always positive because we're in a squared metric here. Mean square error is next here. That's my what? Give me a synonym for mean square error. 169 is what? Residual variance, ding, ding, ding. So that's how much variance in income is left over after controlling for age in my two age slopes. So yeah, on the whole, the model is working. Do I have a significant model? Yes. How good is it? Significant. Well, is that just because you have 734 people? Probably. Okay, how good of a model is it? R square. It's 11% good. So R square you can think of two different ways. The most straightforward is probably as a proportion. 11% is the proportion reduction in residual variance relative to an empty model with no slopes in it. Proportion reduction in residual variance. So age is responsible for 11% of all the reasons why some people make more money. That leaves 89% up for grabs, give or take. So R square is an effect size that goes with my F test statistic. The other way to think of it is because this is a squared correlation. So if I unsquare it, take the square root, it's 0.34-ish. So what is that the correlation of, if I think of this as a correlation?
Age and income?
Close. Income is one of them.
Income and, I don't know, time? Maybe I'm just making that up.
It's related to age, but it's not age. Because if I just correlated age and income, that would be a linear relationship. But age is part of it. One of the columns that I'm correlating is Y. The other is Y hat from age. Yeah. So the correlation of the income predicted by linear and quadratic slopes of age, the Y hat that's created by my model, is correlated with my real income by 0.34. So this is not the same thing as a Pearson correlation between age and income, because that would be linear age all by itself. This is the correlation between income predicted by linear and quadratic age with real income. And because these linear and quadratic slopes work together, like the whole time you need both of them to figure out what the predicted linear slope would be, I don't think it makes sense to pull them apart and get separate effect sizes. I don't. So I would put them together to talk about. I'd say, yeah, I know that we need the quadratic effect because this coefficient is significant. So I know that it's nonlinear. But in terms of how age relates to income, I need both of them working together to tell me that. Yeah, exponential pictures is next. Okay. How are we doing?
I have a question.
Hit me.
On slide 28, where you showed us the first graph, the wild graph.
The
and you
wild
said-
graph. This one?
Yes.
Yes.
And you said that looks like a quadratic to me.
Yeah.
So then we jumped into the quadratic things.
Mm-hmm.
If you were a novice and you couldn't see that, would you just keep trying models until one had a good P and R value?
Quite possibly.
Yeah.
You'd have to fess up to the fact that you're doing sort of exploratory data analysis by adding terms, but that's not an unreasonable thing to do.
Okay.
Generally speaking, I think it's a good idea when you're dealing with quantitative predictors to bring to bear both sort of a theoretical expectation as to how these things should be related. Like, is it reasonable that it would go up and come back down? And also just looking at the data, like the pattern of means, just the association between the mean income and age looks bendy to me.
Mm-hmm.
You could also add age cubed, age to the third power, and that's known as a cubic model. And that creates a model that comes back up again, like an S-shaped sort of thing.
Yeah.
And there's many other types of nonlinear functions that are possible. It's just that when you do it this way, you can fit it in a regular general linear model, and you don't need special software or estimation for it.
Okay.
But yeah, if the quadratic slope's p-value is significant, you know that it helps beyond the linear and that you should keep it. Whether or not it helps like as a strong effect size is still the same issue though, right? Because its significance test is based on effect size and sample size at the same time. Yeah, but to me this looks quadratic-y. Other questions? All right, let me see where we at. Pictures. This is what exponential would look like. So just to show you. These pictures were created by taking time on the x-axis and taking the log transformation of it. And so down here, the x-axis is log transform time, and the black line shows that it's a linear effect. But if you unlog it, exponentiate it back to the original time metric, it creates this bendy curve. And then you can then you can combine log time and square it, and it creates these sort of deviations from this. So this is a way to create a curve that looks like it shuts off as opposed to comes back down, is to take the log of the predictor first. So that's yet another set of possibilities, and you can look at the R-square for a model that does this versus an R-square for the other model and see, which it seems to prefer. Okay, 246. I'm not done yet. Hooray. Do you want to see how to make SAS and Stata and R do this for us? You think so? Yeah, you do. You do. All right, let me get the handout thingy here. Okay, so we are in example 3. We are several pages in example 3. I want to say page 9-ish. Let me get to where we are.
I'm on
Nope,
page
6.
7. Okay.
6, yep. So we finished up the group stuff. Here's my results paragraph about the differences as a function of income group. And now we're starting syntax to center age at 18 years. So you already know how to do this, but just to review, we're centering age at 18 so that 0 means something. If we left age uncentered, then my intercept and my linear slope would be for what kind of person? If I forgot this step, and I just put in age uncentered into my model, then my intercept would be for what kind of person?
A baby?
A newborn. Exactly. Now that's not wrong, but it sure is weird to predict income in a newborn.
Hopefully babies aren't making money.
Well, maybe the child's an actor
There you
or
go.
something,
Or
right?
model.
And by newborn, I mean a 3-month-old baby that they've cast as a newborn. Because you look at the babies on TV and it's like, yeah, that's not what a newborn looks like. They look like little aliens. Like skinny little screaming purple alien, right? That's a newborn. But anywho, we don't want to predict income in a newborn. That's weirdness. So any value of age that we actually have in the sample would be a reasonable choice. I picked 18 because I like to think of the curve as sort of starting and then heading further in time or further along the thing. So I picked the minimum. So I'm going to show you 2 models, a linear only model and then adding a quadratic component for precisely the reason that you asked. Like in real life, if you don't know what the right answer is, you might proceed this in more of an exploratory stepwise kind of way. So it's a reasonable thing to start with a linear model and see if there's any additional curvilinearity that you need. So here is the syntax to do the centering of age in all 3 programs. The common denominator, the term to the left of the equal sign, is the new variable to be created. If you pick a name that's already in your data set, you will write over it and ruin it. And then you have to start over and re-import to get it back. Yep, did it, done it. Yep, been there, done that, got the t-shirt. So I'm calling this age 18 because to me that means age centered at 18. You can name it whatever you'd like, but I encourage you to make names that are meaningful to you and also short so you can type them easily. Then how am I making it? The variable that is to the right of the equal sign is the one that's already in the data. So age is a column I currently have. I am subtracting 18 from it to move the 0 to be age 18. Okay, any questions on that? So I think that my 4-step process that I described for grouping variables actually works for any analysis. Step 1, make whatever variables you need. Step 2, put them in a model. Step 3, figure out what else you want to know from the model and ask for it. And step 4, get effect sizes. I think that works for everything. So this is step 1, make the new variable. The only time that you would not need to make a new variable is if your variable already has 0 as a meaningful value and you're not dealing with groups. Otherwise, you'll make a new variable. So putting a linear effect of age in the model only. So this is something you already know how to do. You did it to look at predicted fits from Please's herd, for instance, in your homework. And we predicted income from education as a predictor or a linear effect before. Now we're switching it out to do age. So proc GLM, income equals age 18. So that's another way that you can accidentally screw this up, is to put the original variable here instead. And if you do that, you'll get the intercept wrong, but everything else will be okay because it changes where 0 is, which is what the intercept refers to. I have some additional statements here demonstrating how I would get predicted income for any age. That is how I got the values that were in this slide here, 29. These sorts of results is these additional types of statements, except that was from the quadratic model. The same thing in Stata. LinCom is how you get linear combinations. And in Stata, the linear slope of age would go after income like this. And in R, I'm using the LM function. Formula equals income, squiggle, 1 plus age 18. And then 3 pieces of output being requested from this model. Get the residual variance, get the results of everything, and then get confidence intervals. And then in R, I'm using GLHT to show how you would ask for predicted outcomes for any age. So this 1 refers to the intercept, and the 12 would refer to the centered value of age at which you want the prediction. Okay, any questions on the code to set up the model? All right, let's see what happened. So in this handout, I only have SAS output because the output looks pretty much the same across all 3 programs, but I have the output from Stata and R in the download folder, so if you want to look along with that at the same time, you can. So I have my model here is the first piece of output. I have 1 degree of freedom for the model. Why is that? Because we only have 1 predictor, 1 slope, exactly. And 182, that's my residual variance. So that's all of the variability in income after being predicted by a linear slope of age. That F tells me that my model is significant. An F of 30 with a p-value that's much less than 0.05, my alpha. How good is it? R square, 0.04, 4% good. Now the results, these 2. So I have an intercept and I have a slope for age 18. So the model says that for what kind of person are they predicted to make $12,000? Who is this for?
18-year-old.
An 18-year-old, according to the model. And then what is predicted to happen as age increases?
Their income
Yep. $200 per what?
Year.
Per year. Yeah. So a slope is the change in y for a 1 unit change in x. If I put that into the story, the slope is the change in income for a 1 unit change in x, means per additional year of age. That's a unit. So people who are 1 year older make $206 more. 2 years older make $412 more, and so forth. And if I take that t of 5.52 and square it, that's my f of 30. 1-to-1 correspondence between my slope significance test and my model significance test, because they are the same. T squared is f if you only have one slope. So yes, age is significantly related to income. Linearly, it accounts for 4% of the variance. So this model says that if I want to be rich, I just got to be old. Right? I hang in there until I'm like 90, and then I make all the money. Anyone see a problem with that? Yeah, not what the graph said. Not what happens in life as a function of retirement, unless you've saved for retirement and invested very well, which, spoiler alert, stock markets are all crazy right now. So maybe that's not even a guarantee anymore. So sort of theoretically, this model is like, not sure that that makes sense, even though it's significant. And if I look at the data don't look like they like it either. Here are the additional predictions I asked for. So these are the predicted income according to the model at ages 30, 50, and 70. And so these are just 0.2 times each additional year of age to get to these. So let's add the quadratic in. So here's my new model. Linear slope stays in. This is a common misconception. People think if I'm going to do a quadratic model, then I just put in age squared. No, age stays. They have to work together. All three programs are going to allow you to directly put in a predictor variable squared without making it in the data set first. The way that I'm teaching you to do this does not require that additional pre-processing step, but the code looks slightly different. So in SAS, I have left age 18 on the model line after the equal sign, and I have added age 18 star age 18. That's an asterisk, the thing above the 8 on my keyboard. So that means age squared, age times itself. In Stata, the exact same thing happens, not with an asterisk, but with that thing right here. This is either a pound sign, if you are old like me, or a hashtag, otherwise. The thing above the 3. And in R, it is yet a third way. This piece right here, capital I, the variable in parentheses with a caret and a 2. The caret is the thing above the 6. So adding in age squared in addition to linear age. So linear plus quadratic age is how we talk about that. Now the rest of these, you do not need these for your homework. This is just bonus material. Like the flip side of the DVD that no one watches that has the director's commentary, that's this. You don't need it to enjoy the movie, but I want you to have it for your lives. So I'm demonstrating in each of the packages how to make predicted outcomes from the model. So the intercept plus whatever value of age we want times the linear slope of age plus age squared times the quadratic slope. So that's where the predictions on slide 29 came from. This is the quadratic model. Same thing in Stata right here with these lincoms. More explicit that we're actually multiplying by those constants and then adding the results together. And in R, it looks like that. So the intercept, the value of age that you want to multiply the linear slope with, and then age squared that you want to multiply the quadratic slope with. The second set then are instantaneous linear slopes at particular ages. So what is the slope predicted to be at later ages? You can ask for this. And the way that these statements are formulated is right here. You start with the linear slope multiplied by 1, and then you need 2 times the age that you want the prediction for. So it's 24 here because I want the predicted linear slope at age 30, which is 12 more than 18 times 2 to get 24. Same thing here in Stata, same thing here in R. So if you wanted to know, for instance, at what point does the model expect the slope to sort of shut off, to become non-significant, you can test it at different points along the edges here. Okay, so for your intents and purposes, just this part, the variable and the variable squared. That will give you everything that you need for your homework. Okay, any questions on the code so far? Yes?
So the numbers next to the age 18 multiply age 18 over 4, it should be calculated by me?
Yes. Yeah, so this number is centered age squared. This number is centered age times 2. Yep, and you have to figure that out based on what age you want the prediction for. Yep. All right, let's see what happened. First stop, how'd my model do? So now I have 2 slopes, 2 numerator degrees of freedom, 731 slopes I could have added, denominator degrees of freedom. My residual variance is down to 168. What was it previously? Let me look at the previous results. 182. So in the empty model, I believe the residual variance is 190. That's all the variance there is. After adding linear slope, it went to 182. After adding a quadratic slope, it went down to 168. Said differently, the R square is going up. The R square reflects the amount of variance that's been explained, the amount of variance that has been reduced of the residuals. So an R square for an empty model, 0. Nothing's explained if you don't have any slopes yet. The R square for the linear age model was 0.04, so it explained 4%, and now we're up to 11%. Well, 11 is better than 4, right? That seems good. Can you think of anything on this page that would tell me whether or not 11 is significantly better than 4? My quadratic model explained 11% of the variance. My linear model only explained 4%. Is 11 significantly better than 4? F is asking whether this is different than 0.
Maybe your T.
Maybe my T. Which T? I got 3 to choose from.
So I think it's the bottom one.
You think it's the bottom one, this one right here?
Yeah.
Okay, tell me why you think that. Because you're right.
Well, because that's the one that's squared, so that's the one that we're thinking about, right?
This is the one that goes with squared age. Yes, so it's no longer the case that T squared is F because there's
T's not squared.
yeah,
It's
age is squared.
Right, yeah.
Yeah. Cough, cough, homework question. So this new slope is what made the R square increase from 4% to 11%. If that new slope is significant, then the jump from 4 to 11 has to be. So let me say this all again because this is easy to get confused as to what is being tested. The job of this F box thing up here is to tell you about the model versus R square of 0. So my F of 47 is, did you get any variance? Yes, I did. How much? 11. Yay me. What I'm talking about is a relative comparison of the previous model in which, did you get any variance? Yeah, I got 4%. Is that different than 0? Yes. Well, if 4 is different than 0, 11 is probably different than 0. The question is 4 different than 11? And I know that because of the thing that I added to go from 4 to 11.
So when we talk about the test statistic, that is negative 7.81.
Yes, it is. The test statistic, or t-value, because even SAS is like, yeah, screw it, I'm not typing out statistic. T-value for age squared as a slope, the slope of age squared. So the slope itself, here's my minus 0.02, divided by my standard error of 0.002 gives me my t. So t is negative because my slope is negative. These are in unsquared original units. T of negative 7.8 is telling me that if the true quadratic age slope were 0 in the population, then this one is like 7.8 standard errors below that. Way into unexpected territory. Would happen less than 0.01% of the time. So yeah, significantly negative. So what's happening then is that we're having a positive age slope at age 18 that is slowing down via the negative quadratic, creating that U-shaped pattern. There, and I answered all my questions, I think. We did R square. We'll do it again. 11% is by how much the residual variance is reduced relative to the empty model. That's one way to talk about R square. The other is a correlation. So the square of the correlation between y and y hat, that's R square. And then here's the extra pieces of information that we asked for with respect to predicted income and predicted linear slopes. And here's my pictures. And here's my words. So this is how I would write up this type of analysis in a results section. I will note that this sentence, it looks like, is in a slightly different order than I normally do it. I put P next to F sometimes, but this one is MSE next. In your homework, you will always know what the correct letter is because it's tied to a value that you would have already gotten correct. So, like, go find, okay, what was 169? Oh, okay, that's my residual variance. That means that I know that MSE is the right thing to stick in front of it. So, F is always first. Then one of these two would be next, and then R square is either at the end of the sentence or someplace else. But everything is contextual. So the same idea in terms of starting with general and then boiling down to specific, I should say. So we fit a model including linear and quadratic slopes for age, in which age was centered such that 0 equals 18. The quadratic age model captured a significant amount of variance in income, F blah, 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 blah. Okay, that's like my gatekeeper to then be able to talk about what happened. Because if the model's not significant, there's not really much point in going forward. The quadratic age model was a significant improvement over a linear age model, as indicated by the significant slope for quadratic effective age. That means, hey, reviewer 3, don't tell me that a linear model would have been sufficient, because here's my test that it's not. Then the model fixed effects. The fixed intercept indicated that at age 18, annual income was predicted to be 2.676. That's my fixed intercept. and was expected to be significantly greater by $1.2 thousand per year of age. That's my linear slope at age 18. Then the twice part. The linear slope at age 18 was predicted to become significantly more negative or less positive, you can say it either way, by twice the quadratic coefficient of minus 0.02, twice. And then the rest of this is just the extra predictions that I did for context. So not so bad. Just square it, multiply the slope by 2, and that's how it changes. All right, questions? And now you can do all of your homework if you want to, or you can pretend that it doesn't exist for another 2 weeks. Your choice. All right, any of that you want to hear again? Or other questions? No, we're good? As good as we need to be at 3:11 on the last class before spring break? So no one will cry if I end 3 minutes early? No? Okay. I want to make sure you get your money's worth. So, all right then. I will call it a day. Thank you all for being here. Let me know if you need anything. Have a great break.
You too.
See you on the other side.
Thank you.
You are very welcome.